So welcome to the first 2420 Peer Tutoring Weekly Review. My name is Les. I work for the Peer Tutoring Center. So we, Peer Tutoring, we do have a convenient flowchart that kind of summarizes what a typical first exam would cover in a standard differential equations course. So you're going to be learning a toolkit of techniques. So by first order, of course, we mean that's an equation that, well, we have an independent variable. So conventionally, we see the independent variable may be called x or t, but of course, it's not restricted to those. And then we're going to have a function of the independent variable that's unknown. So we call that y. So y is a function of x, if you will, a function of t, depending on what we're calling our independent variable. And so a first order differential equation is an equation that involves y and its first derivative. So first order differential equation, ordinary differential equation, involves y and the derivative of y with respect to the independent variable. So let's just stick with, for now, let's just use x as the independent variable, so dy dx. And possibly some other functions of x, so we can call them p of x, q of x, or whatnot. So the way we're going to first organize these first order differential equations is by writing the derivative of our unknown function y with respect to x on one side, and then just having some expression that involves x and y on the other side. So we call that a function of x and y. And we can categorize a lot of these first order differential equations by the form that the right-hand side takes. So, for example, the simplest, probably the first type of differential equation that you've learned about even before this class, possibly, is the separable differential equation. So separable means that, let's say, the right-hand side can be factored into a function of x times a function of y. So suppose that on the right-hand side, we can rewrite this as a function of x times a function of y. If you could do that, then we could separate the variables. So I'll kind of write the more abstract thing alongside the concrete example here. Okay. So you have y prime on the left is equal to some function of x and y on the right. But notice that we can factor a y as a common factor there. And if you can factor the right-hand side, then we can separate the y's and the x's, or the y's and whatever the independent variable is called, on either side of the equality. Divide both sides by h of y, leaving the dy on the left side, and then move the dx over, so to speak, to the right. So over here, we can divide both sides by y, assuming y is non-zero. Let's just say move the dx over to the right. So we see that the two variables have been separated on either side of the equality. We have the y's on the left, the x's on the right. So once you separate the variables, then what you see, you have two differentials which are equal. Okay? A differential on y on the left and a differential on x on the right. And so if you anti-differentiate both sides, the results will be equal up to a constant of integration. And so I know these are kind of, we're thinking the anti-differential of both sides, so that constant of integration is sort of implied. But I'll just write it out so it's explicit, we don't forget it. So in our example here, just anti-differentiate both sides. So we get log of the absolute value of y on the left, and on the right, just anti-differentiating the polynomial. Here's our constant integration. So right now you see that we have at least a equation that relates y and x, right? And it's a general solution curve. General in the sense that we have a family of curves which differs just by a constant of integration, right? The arbitrary constant. That's called the general solution to the differential equation. And then if we wanted to, we could solve for y explicitly. In other words, we can say that y is some function of x, right? We can't always do that, but in this case we can, because we can exponentiate both sides. So the two equal sides become exponents in our exponential, or become the argument of our exponential function. Of course, the reason to do that is because the exponential and the log are inverse functions of one another, so I'll just get absolute value of y. And over here, I'm going to be careful. I'm going to use properties of exponents. So I'll write this as e to this. I'm going to lump this together, and then times e times e to the power c. Now, that's by properties of exponents. So what you don't want to do is think of if you have this exponential plus a constant, you just think, well, that's just my exponential plus a constant. This is wrong, right? These are not equal. It's by properties of exponents. Like here we got the plus constant of integration, but then we exponentiated both sides, so now we have e to something plus something, so we have to use properties of exponents correctly. So now, since c is arbitrary, and we know that an exponential function, at least for real numbers, always returns a positive number, we can just say call e to the c some arbitrary, let's say call it a arbitrary positive constant. And this is maybe too much detail for your own good, but you should at least do this once properly. Okay. So we can write that the absolute value of y is some arbitrary positive constant times this exponential. And so then if we drop the absolute value, we know that then y would be plus or minus the right-hand side, because you're taking the absolute value of y. So it strips away the negative sign if there is one. And since a was arbitrary positive constant, plus or minus a is just an arbitrary constant. So let's just call that b. Yeah. So here we have a general solution where we explicitly solve for y. Okay. And if you had an initial condition, so sometimes they give you that differential equation, and then they say that, you know, y at 0 is some number, let's say 5, right? So that's called an initial condition. And the differential equation, together with an initial condition, is called an initial value problem. What it allows you to do, it allows you to take the family of solutions, the general solution, and pluck out the one function which satisfies that initial condition. So to solve the initial value problem, we have to use the fact that we're given something like when x is 0, right? Of course, this is x. We see that y must be 5, which allows us to replace x with 0 and y with 5 in our general solution. So y is 5, b equals 5. And so now we see that to solve our initial value problem, we found the value of that arbitrary constant using our initial condition. So this comes from the family of solutions to the differential equation. but it also satisfies the given initial condition. Okay. All right. So separable is one of the simpler, I guess, differential equations. The only difficult part might, a difficult part might be, besides noticing that it's separable, might be to do the actual integration, right? So all the techniques you learned in calculus for integration might come into play here. So next, we're going to move on to another type of first-order differential equation. So that's a homogeneous differential equation. Use first order here. So let's again write it in the standard form where the derivative of y with respect to the independent variable is equal to some function of x and y. However, if we're able to think of the right-hand side not just a function of x and y, but rather a function of the ratio of y to x. So if we write the right-hand side as a function of the ratio of y to x, then we call this, well, I mean, it's an often used word in math, but we call this, let's call this a homogeneous differential equation. Okay. So here we have that the derivative of y with respect to x is equal to some function of x and y. However, notice that if you look at all the terms on the right-hand side, if you look at the combined degree of each of the terms, so the degree of x squared times y, if you'd like y to the 1, the combined degree is 3. Right, 2 plus 1 is 3. And the degree of y cubed is 3. And the degree of the denominator is also 3. The combined degree. So x times y squared, or if you'd like x to the 1. So that's 1 plus 2, the combined degree is 3. So if you have that kind of situation, that's a telltale sign that you have a homogeneous first-order differential equation. And what we want to do is then re-express the right-hand side as a function of y divided by x. So towards that end, I am going to divide top and bottom of the right-hand side by x squared, or x cubed, rather. So distributing, simplifying, we're going to get the numerator, we're going to get y over x minus y cubed over x cubed. So let's think of that as y over x cubed. And then the denominator, we're going to get y squared over x squared. So that's y over x quantity squared. So you see that we can think of this as a function of y over x. This is a function of z, where we have z minus z cubed divided by z squared, where z happens to just be the expression y over x. All right, so once you recognize a homogeneous first-order differential equation, you're going to do a change of variable or a transformation by doing exactly what we did over here, right? So we're gonna let z equal to y over x. Simply lump that expression y over x into a single new variable z. So then we can think of this as y being equal to x times z. Right? I just multiplied both sides here by x. So next, what we want to do is complete the change of variable. And so what we want to do is replace all instances of y and the derivative of y with instances of z and the derivative of z. So we're kind of changing out the dependent variable. Here we have y. Y is a function of x, so z must be a function of x. So x and y are both functions of x. So when we find we're going to find dy dx so that we can complete a substitution, right, in a differential equation. Here we not only want to replace y, but also dy dx. We're going to have to use product rule. So we're going to differentiate our product with respect to, or we're going to differentiate the first factor with respect to x, leaving the second factor alone, plus leave the first factor alone but differentiate the second one with respect to x. Now the derivative of x with respect to x here is of course 1. And since y is not a known function of, y is an unknown function of variable x, so z is also unknown. So the best we can do over here is just leave this as the derivative of z with respect to x, since we don't know what z really is. Exactly what kind of function z is. All right, so now notice that we can complete the substitution, right? Y over x on the right will be replaced with z, because they're equal. Dy dx on the left will be replaced with what it's equal to. So if we look at the original, let's rewrite it very quickly. So dy dx will be replaced with z plus x times the derivative of z with respect to x. On the right-hand side, the y divided by x, of course, is replaced with z. Okay, so for our particular example, dy dx using product rule is equal to z plus x times the derivative of z with respect to x. So here we go. All these guys just become z, and on the right-hand side, dy dx is replaced with what it's equal to. And so you're going to get on the left z plus x times dz dx. On the right-hand side, we get z minus z cubed. Now, if you do have a homogeneous differential equation and you do this change of a variable or transformation, you will invariably get a separable differential equation. So notice that I can subtract z from both sides. I can simplify, I suppose, the right-hand side in this particular example. So that would be 1 over z. Well, you know what? Let me just combine these. So multiply the top and bottom by z. Squared. So now we see that we can bring all the z business to the left side of the equality by dividing, and bring all the x business to the right. Hi.
Is this for differential equations?
Yeah. I'm in the middle of recording the review, so I guess let me just finish up this example, and then you can ask me questions if you like. All right. So now that we've separated the two variables on either side, we have two differentials which are equal, so we can anti-differentiate, and the result should be equal up to a constant of integration. Okay. And I'll go ahead and complete this example later, since this is kind of weird. All right. So what's going on?
Wait, so does this review start at 11:30, or what time does it start?
It says 11 a.m. What does it say on the website?
Yeah, I don't know. I got an email from my professor, and he was like 11:30. So. Right, never mind. It's at 11. I'm just done.
Cool. Well, awesome. So in that case, I was reviewing just first-order linear differential equations and all the different kind of techniques you use to solve them. And I started with separable differential equations, and then I went on to homogeneous. So I guess maybe you can fill me in into what kind of techniques you've learned so far.
We learned that, and then yesterday we learned Identities. Yeah.
Right, so in peer tutoring, we have this kind of this flow chart. So let me show you what we kind of summarizes the first order differential equations. And it's kind of like a summary of what you expect on a first exam, right? So you have these different types of differential equations. We have separable, we have homogeneous, or if it's homogeneous, I forget which one is the correct term. We have first order linear and Bernoulli. And for each of these types, once you recognize it, right, there's a technique you use, either a transformation or some technique, which will turn a differential equation into something you can do. So, all right, so maybe you can tell me what is a separable differential equation?
I think it's just like dy dx equals some function,
Mhm.
and turn it into x and y.
Yeah,
Move all of whatever variables on one side.
that's right. So what we have is just one way to kind of think of the conventional form for these first order differential equations is to have the derivative of the unknown function on one side and some function of x and y on the other side. And if you happen to be able to factor the right-hand side as a function of x and y, as a function of x and then times just a function of y, I should say, then you can separate the two variables on either side of the equality, right? You can have all the y business on the left and all the x business on the right. And so once you have these two differentials which are equal, we know that if you take the antiderivative of both sides, the results will be equal up to a constant of integration. And these are indefinite integrals, so it's implied that there's a constant of integration, but I'll just write it explicitly so we don't forget. So the example that I gave was pretty simple. Kind of wrote it in that conventional form where you have y prime on the left and a sum function of x and y on the right. And if we notice that you can factor out a y, we see that we can think of the right-hand side of as a function of just x times a function of just y, where the function of x is x squared minus 1. The function of y is just y. So this will allow us to separate the variables. We'll divide by y to get the y on the left. And it will kind of, I guess, loosely speaking, multiply both sides by dx. So that we have separated the variables. The y is on the left, x is on the right. And once you do that, you just anti-differentiate. And these two anti-differentials will be equal up to a constant of integration. So what do you call a solution or family of solutions that have that arbitrary constant of integration? General, right? It's a family of solutions that satisfies the differential equation. And here we have an implicit solution for y. So we have an equation relating x and y. Can we explicitly solve for y in this case?
Yes.
Yeah. Right, because we can get rid of the log by exponentiating both sides. Of course, knowing that the exponential and the log functions are inverses. Now, I'm going to write something that's wrong. This is wrong, and do you see why? Okay. So the problem is that I'm raising both sides become like the exponents, right? So this is wrong. Let's make sure I cross it out so nobody gets the wrong impression there. So the whole right-hand side becomes the exponent in my exponential. So including that constant of integration. Right? So what we can do is we can think of this as like, you know, the property of exponents. We have to use this. Okay. So we can lump this into this term plus another term, and that's on the exponent. So the correct thing to write is e to the first term times e to the next term. So that's different because now this constant, this kind of, well, c is arbitrary constant. So e to the c will be what kind of thing? It'll be arbitrary still, but it'll be an arbitrary positive constant. Okay, so we can maybe call it b or something. So on the left, of course, the exponential and the log composition inverse is there, so you got y, absolute value of y, and then e to the c becomes an arbitrary positive constant times this exponential. Right. So what's going to happen next is we're going to simply, can you see that by the way, or is it too small?
It's good.
So then you can get rid of the absolute value. And when you do that, you know, if you have absolute value of y, say, equals to 10 or something, you know that y could be two possible values, right? Positive or negative. So here it's plus or minus b. Okay, so since b was a positive, arbitrary positive constant, what can we say about plus or minus b? That's just an arbitrary non-zero constant. So this is a very long-winded way of kind of saying that the absolute values didn't really matter. So let's just call that a. Okay. So here we have an explicit solution, general solution. Explicit because of this function, y, which is some function of x. We're given y as a function of x explicitly.
I have a question.
Mm-hmm.
Why are we like allowed to get rid of the plus minus?
Oh, because I lumped this. Like, you know, like in math, you go along and if you have arbitrary constants, you keep lumping them together to get a new arbitrary constant. So I decided to call the plus or minus b, where b is positive, an arbitrary constant because now a could be positive or negative.
But so when we have like initial conditions, whether it's positive or negative, it depends on those initial conditions, right?
Yeah. So right. So this is just a differential equation right there, right? But we could have been given an initial condition. So like this unknown function, we might be told that when x is 0, this unknown function is equal to 5 or something. So that's your initial condition. And if you have your differential equation together with your initial condition, that's called an initial value problem. Of course, this, since y is a function of x, that 0 represents an x value, and that tells you when x is 0, y is 5. Okay, so if you do have that initial condition, you can take the family of solutions, which is the general solution, and pluck out the specific curve, if you will, that satisfies the initial condition. So we suppose we have that. So this just gives us license to say that, you know, when x is 0, y has to be 5. And obviously that says that a has to be 5. So now Using the initial condition, we solve for the constant. Now we have a solution that's not general, but it's specific to the initial condition. So we solve the initial value problem. All right. I mean, that's the only thing that would be difficult about separable differential equations is to recognize that you can actually separate variables. And the other part is just having all the techniques of integration at hand. But otherwise, it's the simplest kind of differential equation, I suppose. So have you learned about homogeneous? I think you told me, but I forget.
Yes.
All right. So the next type of thing we'll learn is where you have dy dx is equal to some function of x and y. But on the right-hand side, we can think of it as, so it's kind of, you'll see a function of a single expression in x and y. So for example, you might see that the right-hand side can be written as not just a function of x and y, but rather of the ratio of y to x. Okay. Or another type of differential equation, you might recognize that you have some combination of x and y. So we'll look at that as well.
Homogeneous and non-homogeneous equations are still like both linear, right?
Well, not necessarily. So we're talking about the first order differential equations, but they could be linear or not. Like, so I guess we didn't talk about what linear is. It's linear in y, and it's so that's a good question. So when we say a linear differential equation, we say that it's linear in y and its derivatives. In other words, if you have y or y prime or y double prime later on and so on, those things cannot be put into functions, right? They can't be squared, they can't be square rooted, you can't have y times y prime. But the only thing that y and its derivatives you can do to them is multiply them by functions of the independent variable x. So the previous examples that we did, if I can scroll, this is nonlinear. Why is it nonlinear? Or is it? Oh no, it's linear. It's linear. Because here we have the derivative of y is equal to some function of x times y. But we don't have anything like y squared. We don't have sine of y, so we don't have y in some function. The only thing we can do to y is multiply it by functions of x or constants.
Okay, so it would be linear with respect to y.
It's with respect to y. So that's implied that it's with respect to the unknown function that we're trying to solve for. Like, so the independent variable you can square, you can put it inside of like log some transcendental function. Okay. So an example of nonlinear would be something like y prime plus y squared equals x, right? So as soon as you do something nonlinear to the dependent variable, it's nonlinear.
Can you explain the difference between homogeneous and non-homogeneous?
So homogeneous for now, because the word is used often in math to mean different things. Homogeneous just means that the right-hand side over here can be written as a function of the ratio of y to x. Okay. But we can talk about, if your professor does later on, homogeneous at different degrees. Okay. All right. So, but the theme is that if on the right-hand side, if you have not just a function of x and y, but you have more structure, you have a function of an expression involving x and y, single expression, then the trend is to simply lump those together, right? Lump that expression into a new variable to simplify the right-hand side. So here we would probably let z equal to y over x. And over here, we would probably let z equal to ax plus by plus c. Okay. So the homogeneous ones are going to be the ones that are over here. So that's homogeneous. And that's what we're going to deal with first. Let me just check if anybody's in. Nope. Beautiful. All right. So let's see an example of this. All right. Let's do these side by side. So here's a differential, first order differential equation written in this standard form. All right. So what we can notice about the right-hand side is that if you look at each term on the right-hand side, this specific example, the combined degree of each term is equal to 3. So the degree of x squared times y, or say y to the 1, right, is 3. Because you add all the exponents together to get the combined degree. And likewise, the degree of y cubed is 3. And the degree of the denominator, x, or x to the power 1 times y squared, you add the exponents to get the combined degree is 3. So if all the terms on the right-hand side there have the same degree, that's a tail sign that you have a homogeneous differential equation. And then your challenge, the challenge is to rewrite the right-hand side as a function of y divided by x. So do you have any idea how we can do that?
Would you try separating it to like x squared times y over xy squared and then minus y cubed over xy squared?
That would work. That would work. I just kind of look at the highest. I just divide top and bottom by the x to the common degree, right? So divide top and bottom by x cubed. But what you're saying would work perfectly fine. Okay. So we distribute and we get y over x minus, and then y cubed over x cubed. Let's think of that as y over x cubed. Stop me if you don't see the algebra that I just pulled off there. Denominator is y squared over x squared. So you see how the right-hand side then, we can think of not just a function of x and y, but more narrowly, right, as a function of y over x. That's homogeneous. And if you ever get a chance, tell me what the difference between homogeneous and homogeneous is. Always forget.
I don't even know.
All right. All right. Okay. So this suggests that we should simply take this y over x, which we see everywhere, and just simply lump it into y over x. So we're going to say let z equal to y over x, which will simplify the right-hand side greatly, right? But when you do a transformation of change of variable in a differential equation, you not only, right, you have to deal with the y prime business as well. So let's now think of this as the same saying as that y is equal to x times z. Right? We're gonna replace all instances of y essentially with instances of z and its derivatives. So we need to replace dy dx. So how do we compute dy dx? Right. So x is the independent variable, let's remember. Always keep in mind, which variable is the independent one and which variables are functions of the independent variable. So here we have, y is a function of x, so z must also be a function of x, an unknown function. So if we express y as x times z, we really have a function of product of two functions of x. And so we have to use product rule. So we're going to leave the second factor alone, say, and differentiate the first one with respect to x, the independent variable, plus leave the first factor alone, but differentiate z with respect to x. Now, we know what derivative of x with respect to x is. That's just 1. So, and what about the dz dx? Can we simplify that? No. Because z is an unknown function of x, because y is an unknown function of x. So the best we can do is just leave it like that. Okay. Great. So now we would complete the substitution. On the left-hand side, we have dy dx, but we know that it equals 2. So dy dx on the left will become z plus x times the derivative of z with respect to x. Now on the right-hand side, we simply replace y over x with z. Okay, so let's do that. So dy dx becomes z plus x times the derivative of z. And on the right, we're going to get z minus z cubed divided by z squared. So notice that we have got rid of all instances of y and its derivatives. Now, if you do this correctly for a homogeneous differential equation, you will have to get a separable differential equation. Right? So in the abstract, you see that we can move this z to the right-hand side. And then we can divide by the right-hand side. And then move the x business to the other side, right? So we've separated z and x on either side of the equality. So if you recognize homogeneous differential equation, and you do the change of variable correctly, you'll invariably get something that's separable. So that's what you should expect. So in our example, subtract z over, and possibly let's just write that as z minus 2 times z cubed divided by z squared. I just combine the two. Make sure that's clear. The two terms on the right-hand side. Okay. So now we can write this as z squared dz, then 1 over x dx. Okay. And then, since we already know how to deal with separable differential equations, right, once we separate the variables, we anti-differentiate both sides. All right. I think the left-hand side we can simplify further by canceling the z. On the right-hand side, we get log of x up to a constant. Now it's just a matter of integration, so I believe this is going to be, what is this? Natural log of 1 minus 2z squared divided by negative 2, negative 4. Yeah, negative 4. So I just did a kind of substitution in my head, right? Okay, and we get a implied solution for z. So, but we're not done, right? We kind of want to solve for z because we eventually want to get the answer in terms of the answer for y. So I'm just multiply both sides by negative 4, and then get rid of the logs by exponentiating both sides correctly. Here's properties of logs. So I'm just going to use the fact that by properties of logs, I can raise this x to the power -4. Properties of logs. And then times e to the c. All right, so we get rid of the logs this way. E to the c just becomes an arbitrary positive constant. Logs. All right. And then let's not forget that, you know, the goal of the original problem was to solve for y. So we just back substitute if z is equal to y over x, we can just replace z with y over x over here. And then we have a general solution implicitly for y, and we can, let's say, even multiply by x to the power of 4. For aesthetic reasons, really, right? So this is a family of curves that implicitly give you, that solve the differential equation. And if we had an initial condition, we can solve for that constant b. So another one that's similar in the same spirit, but it's unless you have questions about homogeneous. Remember, homogeneous will be turned via that transformation here, will necessarily become separable.
So, if we solved it for x instead of z, would that be okay too?
Sure, it's sort of, you know, really we're looking for some relationship between x and y that works with the differential equation. So it's just kind of conventional that we think of one variable as independent of the other variable as a function of that. But there's nothing wrong with me thinking of x as, or y as the independent variable and x as the unknown function of y. Right, it's just as, yeah, right. If I could get an example, I don't know. But yeah, so same theme, but it's not homogeneous differential equation. But here you have dy dx is equal to some function of x and y. But however, we can just think of, if we can get this to be a function of some combination of x and y up to a constant there. Again, we can just use the theme that we're going to lump this complicated expression into a single new variable, z, say, to simplify the right-hand side. So, for example,
Wait, I have a question about the previous example.
Yeah.
So, maybe I solved it.
I forgot to put on my math. I apologize.
Can you explain the part from 1 minus 2b squared equals bx and negative 4? Can you explain that part again?
This part over here?
No, it's like right under where you did e to the power of everything.
This part?
No, underneath that, like right underneath that.
This?
Yeah.
Okay. So in the line above, we have so here these cancel each other out as composition of functions. Over here, I used, first of all, properties of exponents. So we write this as e to the log x to the negative 4. Now, I don't need the absolute value because that's an even power. And then by properties of logs, properties of exponentials, you can write this as e to the first term times e to the second term, where e to the c is just a new constant. So I just call that b. And then b is an arbitrary positive constant, so after I drop the absolute values on the right-hand side, b just becomes a new arbitrary constant. And then the exponential and the log go out. Oops. Okay.
But okay, so why do we solve for the, like, shouldn't we be solving for y?
Yeah, I didn't give you this is not an explicit solution for y in terms as a function of x. It's an implicit solution that relates x and y. So it's an implicit solution. So sometimes you're able to solve for y, other times you're not. Here we could if we wanted to. So we could say that y squared is equal to b minus x to the 4 divided by negative 2x squared. And then y would be plus or minus the square root of that business. And whether it's plus or minus, if we had an initial condition, would depend on that initial condition. Okay. So for example, y of 1 is equal to, so this is actually a good example. So y of 1 is equal to negative 2. Can we find an explicit solution for y? Right, so right now y is plus something or it's negative. But once you have an initial condition, you can, it's one of the two. It's not both. It's not one or the other. It's one, well, it's one or the other, but not both, right? So how do you determine whether you get plus or minus? Well, use the initial condition. So when x equals 1, y has to be equal to negative 2. So clearly the b minus 1 over negative 2 has to equal to 4. Okay. So b would be negative 7. But for our solution to the initial value problem, then, would you choose plus or minus? Is it plus or minus? It's one of the two, but not both. Which one is it? It has to be minus, right? Because the initial condition states that y is negative 2 when x is 1.
Can we also think of it like, since everything that's in the root, like it has to be a positive expression, since it's like the square root of something. So then we know that whatever's outside, like the sign outside has to be negative.
Yeah, so the square root function always returns a single value for an input, right? So, and by definition, the square root function of real numbers, always positive, non-negative real numbers, returns a positive value. So y is initially negative, we have to explicitly include that negative. The square root always returns a non-negative number. So now I think we'll just do the last one because somebody's coming in later. yeah, we're going to do this type of thing. So here's an example. dy dx is equal to, and we're going to use sine. Why is that so thin? Sine x minus y plus y. Right, so it's kind of like, well, I don't know how to deal with it. It's not separable or anything. So let's just try to simplify the right-hand side by simply calling this linear combination of x and y up to a constant. Let's call it a new variable z. Seems like a natural thing to do, right? That's well. Okay. So what we want to do is then just complete the change of variable, but to do that we have to replace dy dx. Yeah. So we're going to differentiate both sides over here with respect to z, x, because we're considering x the independent variable. So the left-hand side differentiate with respect to x, and the right-hand side differentiate with respect to x. Of course, the derivative of a constant is 0. Right. So now notice that we dy dx would be the same as 1 minus dz dx. If you just do a little rearranging. And why am I trying to solve for dy dx? So I can directly substitute for it in the original. So if you solve for dy dx here, you can directly see what the left-hand side becomes. So on the left-hand side, dy dx is equivalent to 1 minus dz dx. And on the right-hand side, it's simpler because this whole thing we decree called z, yeah? So what kind of differential equation is this? Or is it linear, by the way?
Yes.
So x is the independent variable. Here, z is the dependent variable. So is this linear in z and its derivatives? No, because of the sign. The z is inside of the sign. Remember, to be linear, the only thing you could do to z and its derivatives would be to multiply by functions of x or constants. So it's nonlinear in z. But this is separable, right? Because I can separate the z's on one side and from the x's on the other. And then you have two differentials which are equal. So again, if you have this kind of thing, where the right-hand side is a function of some combination of x and y up to a constant, if you do this transformation correctly, you should end up with a separable differential equation. So this becomes separable, and you know how to deal with that. So we continue the job. Anti-differentiate. And over here, you just have to use the correct integration technique. I guess we can try to introduce one of the trig identities, you know, sine squared z plus cosine squared z equals 1, by multiplying the top and bottom by the conjugate of 1 minus z, sine z. So this is just like the laborious part where you just have to review all those integration techniques. Or use Wolfram alpha or something. So, So if you ever have questions about how to integrate something, you can always drop by the tutoring lab downstairs if you've seen it been there before. Right, so the idea then, by multiplying by conjugates, I in the denominator I introduced 1 minus sign squared, which then can be replaced by a single term via the so-called Pythagorean trig identity. Right, so the denominator will become cosine squared. And I think that should be easy. So that's 1 divided by cosine squared is secant squared. And then this becomes just itself. So. Okay, so what's the antiderivative of secant squared? Okay. And the antiderivative of sine over cosine squared would be 1 over cosine. Negative, or yeah, 1 over cosine. So if you wanted to do that one, I guess you would do a substitution where u is equal to cosine. Du would be equal to the negative of sine. Easy. So then we see that the denominator would become u squared. The numerator would be the negative of du. So that would give us, by simple power rule for integrals, so that simplifies to 1 over u up to a constant, where u is cosine. Right. Cool. And then maybe you can simplify, maybe not. But I think it would be very difficult to get an explicit solution for y. But let's not forget to just back substitute. What is z really?
X minus 5 plus 5.
Yeah. So good luck trying to solve for y explicitly. Sometimes you just don't bother, you can't, right? So in the instructions, they might even say just find an implicit solution. So be on the lookout for that so you don't waste time. Okay. Well, it's past 12:15. There might be some other people coming in for another review. So I didn't get the first order linear differential equations, and I didn't get to Bernoulli. But if you have questions right now, you can come back downstairs with me. And have you been there before, the tutoring lab? Basement of the McDermott Library?
Yeah.
Yeah. So you can always ask questions there.
I have like a quick question.
Mm-hmm.
It's about like the first order. I think it's non-homogeneous where you use the mu and stuff.
Yeah, first order linear. So something like, so if I write it in the standard form, it would be y prime.
So it's just like, I understand it, it's just like a technical question. So
Yeah.
our professor has like some pre-done notes as well as like notes that we take during class.
Yep.
So this is like what he showed us for like this formula
Yeah, that's right.
where you add the c before you integrate, but like in class he would just do the integral and add the c at the end. Which way is like better?
Oh, yeah. So if you write down the formula, you sometimes write plus c just so people don't forget that it's there.
Yeah.
So if I have a solution you already found the integrating factor. We can write it as 1 over the integrating factor times the integral.
dx mu x.
Yeah, or yeah, A, so if your professor uses A and B, that's also fine. That's depending on where part of the world they come from,
So
right?
it doesn't matter if you put that c before or after, so long as you remember.
As long as you remember it. So you'd have this antiderivative of the right-hand side times the integrating factor. And you can leave it like that because it's implied if you have an indefinite integral, there's a constant of integration. But students forget, it's very important. So professors in the formula will often just explicitly write that constant integration.
Like honestly, I was just wondering because if we had like one really special case, if this problem, do you see how like the integrals like cancel out, so then you wouldn't have like a plus c?
But
It's like a
no, it's still an indefinite integral. There's still a constant of integration.
even if the integrals cancel each other out.
Yeah. Yeah. Like, so the antiderivative, what's the antiderivative of 0 dx? No, it's a constant.
Oh, okay, sorry.
Right, so as you still have that arbitrary constant. Remember, the derivative of the constant will give you the 0, right? The thing you're integrating. So,
That makes sense.
right. So in the formula, they just write that down, even though if you didn't have to, because it's known that an indefinite integral would yield a constant integration, but so you don't forget it.
Okay, I was
And it's-
confused about that. I guess I just forgot that the integral here is.
Yeah.
Okay, thank you so much for today.
Yeah, sure. Good luck.